Welcome to the third video in our Class 6 series of instructional lecture note videos. So in this video we'll take you through the next most complicated rotational versus energy diagram process, which serves as a good analogy for other conformational analysis problems. So let's consider trying a conformational energy diagram for butane. First, it's important that we choose to cite down the carbon-2, carbon-3, the C2-C3 bond. So we've drawn our imaginary eye looking down the C2-C3 bond of butane. There's 1, 2, 3, 4 carbons in this molecule. And I've labeled this methyl group CH3A. And you can see it's pointing straight down on our Newman diagram for this staggered conformation of butane. HB is pointing up and to the left because it gets the wedged bond, and HC is pointing up and to the right because it gets the dash bond. This fourth carbon in our molecule, that methyl group, is pointing straight up, staggered between HB and HC. And then we have these two hydrogens respectively on our staggered conformation. Now we call this an antiform of butene because the methyl groups are opposite each other. We'll also define this as 0 degrees in reference to our energy versus rotational diagram. If we rotate the front by 60 degrees in a counterclockwise sense, we get this eclipsed form of butane. We'll call it conformation B. If we keep rotating the front, the C2 carbon like a propeller, another 60 degrees to get to 120 degrees in conformation C, we get this staggered conformation of butane. And we'll call this the gauche conformation of butane. You notice that it's different than the original staggered conformation of butane that we started out with, the antiform, because now the methyl groups are not pointing opposite each other, they are right next to each other. So they have a dihedral angle of 60 degrees. If we keep rotating that front carbon-2 like a propeller in a counterclockwise sense, we reach 180 degrees, and we'll call this conformation D. This is another eclipsed form, and this eclipsed form is different than the eclipsed form B that we saw at 60 degrees. We'll continue rotating the C2 carbon in a counterclockwise sense to get to the 240 degrees relative rotation from where we started. We'll call this conformation E, and it is also gauche, just like C. So we would expect the same energy for this conformation at 240 degrees and as the conformation at 120 degrees. We continue rotating that C2 carbon counterclockwise another 60 degrees to get to 300 degrees. We call that conformation F. It is a eclipsed conformation, and it is the same in energy as our 60 degrees eclipsed conformation. And finally, if we continue rotating that C2 carbon another 60 degrees, we get back to 360 degrees, which is 0 degrees. So before we go to an energy versus rotational diagram process, I thought I would just comment, not all staggered conformations are the same, not all eclipsed conformations are the same. And I thought I would take you through what this looks like with an actual molecular model. So here we have butane, and here we're going to cite down the C2-C3 bond, and there is a staggered conformation of butane, citing down that C2-C3 bond. And we'll go ahead and rotate it. Here's an eclipsed conformation where we have two hydrogen methyl eclipsing interactions and one hydrogen hydrogen eclipsing interaction. And here we have a gauche form of butane. We continue rotating it. This is a different eclipse conformation where we have two hydrogen-hydrogen eclipsing interactions and one methyl-methyl eclipsing interaction. Continue rotating it. We're back to a staggered conformation, and this is a gauche conformation. We continue rotating, and we reach an eclipse conformation where we have two methyl hydrogen eclipsing interactions and one hydrogen-hydrogen eclipsing interaction. And finally, we're back to our starting position with an antiform of butane with the methyls pointing opposite of each other. So, if you bought a model set, you can try that. We can see that this is like a bond line structure, and of course it's a staggered conformation. What would the bond line structure look like for eclipse? It would look like this. So that is the high energy eclipsing conformation. All right. Last page for this video. Here is the energy versus rotational diagram process. So you can see A is our lowest energy staggered conformation. B is higher in energy than A by about 3.6 kcals per mole. We go down to the gauche staggered conformation C, which is higher in energy than A by about 0.9 kcals per mole. Our highest eclipsing conformation is conformation D, and that's higher in energy than A by about 4.9 kcals per mole. E has the same energy as C, F has the same energy as B, and 360 degrees is the same as 0. So conformation A is the lowest energy staggered conformation, in which the methyl groups are anti, pointing away from each other. And you can see I've drawn what the bond line for the highest energy eclipsing conformation would look like. It looks like this D bond line. Staggered conformation C and E are both gauche, and they are higher in energy than the anti-conformation by about 0.9 kcals per mole. So that pretty much concludes this video, and we'll see why these conformations are important when we look at cyclohexane conformers and consider other energetics for these interesting organic molecules.